Welcome back. In today's video, we want to simplify the following expressions using phasors. So the first expression is I1 of t, which we're going to call 1. And we could have used, in this case, we could use the trigonometric identity or the sum and difference for cosine and then simplify that down. But it's easier to transfer that to the phasor domain and manipulate. So the first thing we're going to use is the relationship between the time domain and the phasor domain, which is a signal x of t is equal to a times cosine of omega t plus theta. In the phasor domain, that's equal to a times the complex exponential e to the j theta. So we go ahead, put that into the phasor domain. So that's 20 times e to the j minus 30 plus 16 times e to the j 15. We then go ahead and use Euler's identity for us to be able to add both of those, which is equal to cosine theta plus j sine theta. We go ahead and we'll see that our expression will give us two cosines and two sines. So we add 20 times cosine of 30 to 16 cosine of 15, and that will give us a magnitude of 32.78. So that's 32.78. We know we're going to have two sines, so if we factor out a j and we add minus 20 times sine of 30 plus 16 sine of 15, we then end up with negative j 5.86. We can then go from here using our rules for complex algebra. We know that in polar form, and let's just use x. So that is the magnitude of x times the complex exponential e to the j theta. The magnitude is equal to plus the positive square root of x squared plus y squared, and theta is equal to inverse tangent of y over x. So this then goes to a magnitude of 33.30 and a complex exponential of e to the minus j 10.14 degrees. And v1 of t is then equal to in the time domain. So we're then using the same relationship to go from the phasor domain to the time domain. In the time domain, this is going to equal to our a, which is 3.30 or 3.3 cosine, and our omega t and our angle is negative 10.14, and that's in amperes. So here we have simplified our first expression. So now on to the second expression, which is I2 of t. And this we'll want to, because in the phasor domain, we need the positive cosine. So we adopt the positive cosine form. So we're going to need to change this into a cosine. And we also need to change this into a positive cosine. So this is 2. So we then go ahead. We're going to use the identity that cosine of x is equal to plus or minus sine of x plus or minus 90 degrees. So that will allow us to change our sign. And for our cosine, so cosine of x is equal to minus cosine of x plus or minus 180 degrees. So both of those identity are going to allow us to put that in the positive cosine form. So we can then go ahead, I2 of t, that's my bad. So that's I1 of t. And I2 of t is then equal to, we convert our 14 sine omega t plus 45. So we then get a positive cosine. So we keep our a, so positive cosine times omega t. And if you subtract 90, so here we have a positive, we had a positive sign, so let's go back to that. We have a positive sign, so we subtract 90, and then we're left with a negative 45. So that's negative 45 degrees plus 17. Now that's a positive cosine, omega t. And here we had a positive 60, so we subtract 180, so we're left with 120. Now we can then go ahead and convert that to the phasor domain using our time domain to phasor domain relationship. So this is now equal to 14 times the complex exponential of e to the j minus 45 plus 17 times the complex exponential e to the j minus 120. Then we can use the same Euler's identity and add our cosine and our sines together. And when we do that, we end up with 1.40 minus 8j, 24.62. So at this point, we can then go back to the same technique that we used earlier and then use our complex algebra relationships and convert that to polar form. So we can get back to the time domain. So in polar form, this is equal to 24.66 e to the minus j, 86.75. So let's call it 86.8. So 86.8 degrees. So we can then convert that to the time domain by using our time domain to phasor domain relationship. And that is equal to 24.66 times cosine omega t minus 86.7, let's just write 75 degrees. And that's in amperes. So the last expression that we have in this case, this is much simpler than the last two. So let's just go ahead and get this done. So in this expression, we're going to use and I don't know what your book column, but they're the phasor domain to time domain relationship. And each of those you can see is given as some coefficient a times cosine or sine. So let's just write them out. So we're going to have, that's 3. So we're going to use, in this case, we're going to use a times cosine, and let's use omega t, and in the phasor domain, that's a cosine, that's going to just equal to a, and then we're going to use a times sine of omega t. In the phasor domain, that's going to equal to a, and I think that's a negative j 90 because we're dealing with degrees. So negative j pi over 2, so that's going to be a negative j 90, and that can simplify to minus j times a. So we're going to use both of these expressions to simplify that. So we can then go ahead, and that's pretty much obvious. So if we go back up here, see our following expression, and then we can say that I3 of t is equal to the first portion of this. So by using our relationship, time domain to the phasor domain relationship, we can say that 2 cosine of 5t is equal to 2. See here, 2 cosine of omega t is going to equal to a, which a is the coefficient 2, minus, and because a sine omega t simplifies to negative j times a is 7. That means the minus is going to turn into a positive or a plus, and it's going to be j7. So here we're in rectangular form. We apply our same complex algebra properties. So we can then go to the polar form. So in polar form, our magnitude is 7.28 e to the J74.05 degrees. In polar form, as always, we go, polar form is still the phasor. We're still in the phasor domain, so we can go from polar form to the time domain. So that is, we keep our magnitude 7.28 times cosine, and omega t in this case was 5t, and an angle of 74.05. So that's 74.05 degrees, and that's in amperes. So this is I3 of t. And that's it for today's video. So I'll see you in the next one. Bye.